KW Physics. I'm Mr. McConley. We're going to do total internal reflection. It's a really interesting concept. And the best way I can start describing it to you is by having you take a look at this glass block. So think of a big chunk of glass. And this big chunk of glass has light already in it. Okay? So, maybe the light came in from up here, but we're not worried about how it got there. Just the light is going through the glass block, and now it's about to leave the glass block, and it's going to go into air, for example. So you're going to go from glass to air. Now up until this point, we've always gone from the lower end value to the higher end value, and this is going to be the other way around. So you know that glass block might have a 1.66 index, and air has a 1, for example. So I want you to look at some various directions that the light could be going. So if you follow the black line hits at the normal. Remember, the dotted line is perpendicular to the surface, called the normal. Hits at the normal, and when it does that, it actually bends away from the normal because you're going into a less dense material. Let me describe that a little bit more. If you follow the black line and continue straight, it would be something like my dotted black line right there. But it didn't continue straight because as it was moving along, I'll show you with my marker here, it's a good technique to use on a test. If I'm moving along like this, which end of the marker hits the barrier between the glass and the air first? The cap end, right? See that? See how the cap is starting to hit? So as the cap starts to hit the air, does the cap speed up or does the cap slow down? It speeds up. Everyone can kind of follow that logic. So what happens is it's going along. Now the cap hits and starts to speed up. So see how it bends that way? Because it speeds up. All right. So now that you agree with me that it would speed up and it would bend away from the normal, you can see that the black line makes sense. What if you sent the light at a larger angle? So now look at the red line, for example. The red line is going along, and it does the same thing. Okay? The cap end of the marker hits the air first, so it speeds up, and it bends this way. So as you can see, as these angles are going this way, these angles are going this way. Fine. Well, then you get to this weird point right here, and I don't know if this is accurate, but let's just draw it right here. If I draw with my blue marker right there, and I come in at this angle, the light is again going to speed up, but you know where it ends up? It ends up right along the surface like this. So it didn't really go into the air, and it didn't really stay in the glass. It just kind of traveled right along the surface. Now we're getting really close to what's called total internal reflection. So, as this angle got bigger, these angles are getting closer to the glass. Now as I go a little bit bigger, like this, the green, you know what happens? It just bounces back into the glass block at the same angle that it came in at. This point right here is called total internal reflection. Total internal reflection. And that green line represents when the light will stay right inside the glass block and not even leave. But back up to the blue line for a moment. One thing I didn't mention about the blue line is the blue line has a special name. Or actually the angle of the blue line has a special name. If we take this angle from the normal over to the blue line, now remember the blue line is the one that went right along the surface. This is called the critical angle. The critical angle. It's critical because it's the point where the light no longer leaves the glass and it no longer goes in the glass, it just kind of hangs at the interface. So that's the critical angle. So you understand the concept of total internal reflection. Now let me just show you the math, which is very easy because it's exactly what we've done before. You know that the sine of theta 1 over the sine of theta 2 is equal to n2 over n1. You know that because you've been doing that. We've called that Snell's law. Now, take a look at the picture again. Let's look at the blue. We're focusing on the blue, okay? If you're focusing on the blue, what is the angle theta 2? From the normal to the blue, what's that angle? And I think you can see it's 90 degrees. This is the sine of 90 degrees. Can you see that? And if you take your calculator for a minute, you do the sine of 90 degrees, or if you're just good in math and you remember, what does it give you? 1. So actually what happens is the sine of theta 2 goes away because it's a 1. It's gone. So if you want to know what the critical angle is, here's all you do. You take n2, you divide it by n1, and you take the inverse sine of it. This angle right here will be the critical angle. You will be able to determine the critical angle. And one more thing, if you know the critical angle, then any angle bigger than the critical angle is going to do what? Green line. Back in the box, which is called total internal reflection. Physics.